and then maybe some causal learning, some more advanced things. But I don't think we saw a case where we sort of thought about how we collect the data set. So this talk will be about if you also allow your algorithm to go out and collect data, which data should you collect? What is the most useful data to get? And how can that sort of, when you put the data collection in the loop, how can you optimize the algorithm with that? All right, so at first I want to thank my collaborators. I've been very fortunate to work with quite a few smart people. There's Remy, who was a postdoc with me for a year, who is now going to work with Francis Bach in Paris. Han, who is now working with Augustin Bloom in Chicago. Emily, maybe you know her. Pierre Menard is an interesting case because he carefully managed to not have any picture of himself anywhere. I was creative trying some Google search terms, image search, homepage, you know, Google Scholar doesn't exist. But it turns out if you don't know who this is, I don't know, try it and you will be surprised. It's a beautiful story by this man about someone who's also called Pierre Menard and who undertakes the project of writing Don Quixote without ever reading it first, but by just really thinking very hard about how it should have arisen. Like 100 years later, he starts, his life project is to write the Don Quixote, and I think at the end of his life, he has managed several chapters from scratch. Okay, and Orléans is also a bandit legend. Okay, so I'm going to do a mortal sin from the start, which is I will start with an intermezzo. I thought, you know, about where to put this stuff, but in the end, the best place to get it out of the way was to start with it. Okay, so we will use what's in here in several places on the way, but I will, sorry, yeah, I shouldn't have done it, but it was the best option. So let's start with an intermezzo. I would not talk about bandits at all, about something else, namely, how will we solve the saddle point problem? Okay? So after this, I will sort of properly introduce what bandits are and what they're for, etc. Okay, so saddle point, what does it mean? So let's say we are given some objective function, g of two arguments, x and y, and we assume it has this nice saddle shape. So it's convex in x and concave in y. Okay? So as you probably know, at that point, we can look at this function as a two-player game. One player controls x, one player controls y, and we can wonder what can these players achieve. Right? If x goes first, you can choose smart x, then y can maybe respond to make g large, and as a result, x can guarantee this value b, and similarly the other way around, y can guarantee actually the same value. Right? So the fact that these are equal is known as the min-max theorem. Conditions maybe, but typically convex concave is sort of the thing to remember. So that's the value, and we would like to find some good x and some good y that actually give you that value. Okay, let's be a little more relaxed. Let's say we're looking for a combination x bar and y bar that give you that value v star up to some small epsilon. Okay, so if you play y bar and you respond with the best possible x, you only undershoot v star by a small epsilon. And similarly, if you play x bar and you get best response y, you only overshoot v star by a small epsilon. Okay, so that we call an approximate saddle point with gap epsilon. Okay, and the question is, how will we find such saddle points? Okay, so this is actually a very nice and classic idea due to Freund and Shapira, which is to say, let's take a regret minimization algorithm and give such an algorithm instantiated one for each player, and let's have these algorithms play against each other. Okay, so these algorithms will output some iterate choice for x and choice for y, and then we have to figure out how we update these algorithms, and we do the following. So for the x player has to wonder, what would I have gotten if I had played a different x than the one that I played? And to judge that, we will keep y fixed, the y that the other player played, and we will just look at what happens if you change x. So this will be the loss function that we feed to the x player, and similarly with the sign change, we feed it to the y player. And then we have these learning algorithms continuously interact and play for a bunch of rounds, updating the same loss function every time. And then at the end, we will average the iterates. So you just do a uniform time average of xt and yt, and that's what you output. Yes, xt is minimizing. So for xt, g is the loss, the higher the worse. For y, it's the opposite. Sorry? Not really alternating. The way I write it here, we just do it sort of in parallel, independent. But if you want, you can order things. We have this learning algorithm. We can make many choices, but we just pick some learning algorithm, and we feed it a loss function. And based on that, it updates and gives us a new xt plus y. Yes, yes, yes. Yes. Although, I mean, it's like a slice in this way of g and a slice in that way of g. That's the loss. Okay, so you run these algorithms for some time and iterate average. Now you can ask both of them, like, what do you predict in this round? You get an xt and a yt, and after that you feed both of them a loss function in which the other iterate features, that's true, but you don't have to order them. It turns out you can actually, and sometimes that's beneficial, but I just want to get sort of the high level idea is these things are just sort of beating on each other, trying to get to better points for themselves, given that what the other did is different. Okay, so now if you assume that these players actually have regret bounds, which in this world means that, for example, the xt player thinks that its own loss is what happens if you take g and put in xt yt, and he thinks that the best that he could have done is still with fixed yt's look for the best possible value of x. Right? So this is what a regret bound would be on. So let's assume that we have a regret bound and that its value is rt for x. Right? And similarly, we're going to assume that we have a regret bound for y. The same up to a sign flip. Right? And if you want to think about numbers, I guess these rt are typically order square root t, right? Or some other sublinear rate. Okay, so that's an assumption. Now, under that assumption, you can show that indeed these iterate averages are a saddle point, and the precision to which they approximate the value is the sum of the two regrets over t. Okay? That's right. So if you want to invert it and see, I want precision epsilon, what t do I need? It's 1 over epsilon squared. Okay? So I just want to flash this. I don't think I should go over it very carefully, but it's sort of one of the most beautiful chains that I know. You know, you use all the things that you have, like suboptimality, the convexity, the regret guarantee, concavity, suboptimality, and you end up sandwiching everything between V and V plus this gap. Okay, so all these things here are gap close to each other, what each player can guarantee. And it's super nicely symmetric, right? There's like the middle here, and then it goes X concavity, Y convexity. Okay. I get excited about these things. All right, good. So we have a way to get approximate saddle points. How do we sort of practically instantiate such a scheme to use it? And it turns out if you want to figure out what are good online learning algorithms, it typically depends on the domain of these X and Y. Right? But I think we saw a bunch of choices, or at least close to choices. For example, we saw stochastic gradient descent, which is very similar to online gradient descent, which is something for which you have this square root t regret bound. that works if you have, for example, a ball as your domain. If it's a simplex, maybe you want to run some version of hedge. Maybe you want to do full regularized leader, perturbed leader. You have a lot of freedom, right? All these things will give you square root T regret. Okay. And then maybe one more nice twist is that if you actually order the players and you think about what can the second player play, the second player sees the move of the first player if you order them. And there are some extra things you can do. You can actually get negative regret in that case. For example, with be the leader, if that means anything to you, or maybe even with best response. You just see the move, you punish it as hard as you can. Right? And we particularly like this one because it doesn't even need any memory. So it's a very nice learner that has... Well, the reason is regret is the best fixed action for you, whereas best response is every round is the optimal action in this round. That's much smarter than the best single fix. Okay, so if in the rest of the talk we will encounter some settle point, what we're going to do is we'll typically pick hedge for the player that plays on the simplex, and then best response for the other player, and then we can get these nice guarantees of approximation. The fact that it's negative here, I mean, yeah, you're right in that you always get the square root T from the first. You save the square root T from the second. So in terms of rates, it's not so impressive. In terms of implementation, it might actually win you a lot. So if this G is a complicated function, and the domain of Y is maybe difficult, then it's often much easier to do best response than to actually build a learner for it. This is the single minimization. You don't need to maintain any uncertainty, which is typically, in the form of a distribution, and then maybe not finite support, blah blah blah. Okay. Good. So that's the end of the intermezzo. Oh, maybe some nice connections. You can do many more things. The fact that these learners are interacting in this way, you can actually exploit that. For example, by adding optimism. And I wanted also to connect to a dinner conversation that I overheard, where people were saying that they finally understood Nesterov acceleration. There has been some marveling at Nesterov going on during the workshop, where you wonder, like, how do they invent it? So I'm also on the lookout for trajectories, how to understand Nesterov things. And so one of the nice papers that I like a lot is explaining Nesterov acceleration as a particular choice for two players that are interacting against each other, and that sort of make careful use of each other's algorithm to actually get the regret much below square root T. Okay, so but that's just a side note for people who like reverse engineering a way to get acceleration. Yes. That's right. But what will happen in the rest of the talk, there will be square root T overheads from concentration and other things already. So everything below square root T is sort of very nice, but not helpful to us anyway. So I'm happy to stop at this square root T boundary. And what is in it for me is the simplicity of actually getting to that settle point, especially based on this best response. Okay, so far so good. So let's start with the tutorial. Okay, so we now have this nice background in settle points. Let's see what the tutorial is about. So I announced in the abstract that it would be about structured stochastic bandits. So here's a nice cartoon for what that means. So suppose you have 3 different forms of treatment, and you assume that there is some model that you don't know that says, given that I give the first treatment to some patient, the probability that the patient is happy is maybe 1/6. Okay, the other option is the patient is sad. 2 things. So the Bernoulli model, conditional on the treatment, and maybe for the second treatment is 2/3 and the third treatment right? And I do not know this model. Okay, so what can I do? I can sort of open a stream of patients. So the patients come in one by one, and for every patient I can say, I need to learn something about these drugs. So let's prescribe one and see what happens. Right, so I give maybe the vitamin pills to the first patient, and I record that the patient is happy. Based on that, I can maybe update what I believe, and I can go to day 2 where I have another patient, completely IID from the same pool. There's no features, nothing, and I prescribe maybe another treatment, and I observe what happens. Right, and I go on like this as long as I want, maybe until someone dies. Okay, so while I'm doing this, I am gathering information about this unknown model here, right? But not at a uniform rate. Like the drugs that I prescribe more often, I learn more about how good they are. Okay, so what are the typical tasks that you can ask your algorithm or your strategy to accomplish? There are actually 2 that I will talk about. So the first is called pure exploration. And in terms of this doctor analogy, what you want to do there is you want to use the trial to cure the people that are not in the trial. Okay, so you want to figure out which of the drugs is actually very good, and then you want to mass produce it for the world. But you don't care about the people in the trial. Right? If it gives you a lot of information to prescribe a very harmful drug, you will gladly do it. You don't care about them. They're just 100 patients, and then the millions, right, come in after. That's one perspective, pure exploration. The other perspective is every patient that we make happy is reward. And we want to make as many patients happy as possible in the trial. Okay, so that's reward maximization, and we'll talk about it in the second half. Okay, and it turns out that the strategies that you need for both of these tasks are very different. Okay, so it may sound similar, but it's not. Okay, so I also talked about structure. So what's structure in this world? Now we need to have some knowledge about how the different treatments relate. Right? So for example, it could be different doses of the same drug. Okay, and then there is again an unknown model that says the probability that you're happy given that you got a small dose is some number, all the way up until the large dose, some probability. And then we might make some assumptions about how this model actually looks. Right? And one typical assumption for drugs is that if you ramp up the dose, initially it works better, and then some toxicity effects kick in and it works worse. Okay? So, for example, you might assume that there is some unimodal mean as you go along the doses. Okay, so that's structural knowledge that we would somehow like to exploit while we do any of these tasks. Okay, and other than that, the interaction is exactly the same. So the structure is not really shown in the interaction. You just, every round you prescribe one of the doses and you record what happens. Okay, so what are we going to do? The idea will be that we like to have efficient algorithms for both of these tasks, pure exploration and reward maximization. Efficient in the sense of computational, but also statistical performance. Okay, and so for that, we will first look at lower bounds that say, whatever smart algorithm you build, it cannot be better than this at its task. Okay, and what we will find is that these lower bounds sort of bottom out at a very specific two-player zero-sum game in both of the cases. So it says at least the lower bound is determined by some two-player game. We could in some sense call it the mini-game. It has nothing to do with the time interaction in the bandit problem. It's just some local little game that if you solve it, you know how hard is your problem. Okay? And then we will solve, so we will build our algorithms for the bandit interaction by actually solving in some sense that little two-player mini-game iteratively in the fashion as I showed you before. Right? With some settle point solver going on. Alright, so let's get to the first task, which is pure exploration. So now we're after learning as much as possible about the state of the world. Alright, so yeah, just to sort of broaden the scope a little bit, in pure exploration, you can ask actually many questions about the world, right? In the example, I asked which of these drugs is the best one, but that was not the only question you might ask. You can sort of write down some question about the world, and you can try to answer it interactively, right? So you prescribe some experiment to do, you do it, you see the outcome, you iterate, and at some point when you're ready to answer your question, you output the answer. Okay? And what we want to do is efficient systems, and we want to understand, in particular, how what we sort of put as the query and what we know about the world affects these algorithms. Okay, so now let's get down to business. No more pictures. Well, the pictures are in the corner. But so what's our sort of model for the environment? So what I will do here is I will fix a one-dimensional exponential family, Bernoulli Gaussian maybe, parameterized by the mean, and that will be my model for what's behind any of my my possible experiments. Okay, and throughout you will see the little d between two means. It will always mean the KL divergence. Right? So for example, for Gaussians, that means square distance. Alright. Then to model the world, we will just assume that there are some finite number of sources of information that I could potentially ask for. Maybe these are the drugs. So that number is known. And behind every one of them, we have to pick the distribution, which is just parameterized by its mean. And that's unknown to us. Right? But that's the true state of nature. Okay? To model the structure, we will say there is a set of possible environments. That's just a subset of all the possible tuples of means. Okay, so that could be maybe unimodal or some other thing. And apart from that, we have to model this query. So for that, we'll introduce a set of possible answers. And we will map every bandit model that we might encounter to the correct answer for that model. Okay. So maybe let's do some examples still. Okay, some pictures there. So the best arm problem. The possible answers there are just the labels of the arms. The best answer mapping is the argmax. And if you look at that for two arms, so you graph the mean of arm 1 here, the mean of arm 2 there, then this best answer map just colors this one with arm 2 and this one with arm 1. Okay, and another problem that I like a lot is called the minimum threshold problem, where the answers are low or high. And you have to answer low if the minimum mean is below some threshold. So that's the green area here. And you have to answer high if the minimum is above some threshold. So that's orange. Okay, so that's some other, I guess, problem where everything is packaged. Yes. So your job in the best arm problem is not to estimate the quality of them. Yes, yes. I just want to know the index of the best, because that's the one I will mass produce. And then the fact that it actually doesn't work, we will never find out. Because we're not asking for that. And these methods will be sort of very much squeezed to not learn anything beyond what you're asking them, right? So you will probably have some remaining uncertainty about actually how good it is. But you will know that it's better than the other one. Okay, so there are many, many other problems appearing in the literature. Just for maybe the connoisseurs, you can ask for the set of top and best, if you like. You can have some combinatorial structure on your arms and ask for maybe maybe the shortest path, for example, based on bandit observations. One that I like is maximum profit, where you have one set of arms that is profit or gains, and one of them is costs, and they are paired, and you want to find the index of the pair with the largest difference. You can maybe, you can take some two-dimensional thing, draw a picture there, and say this is what you have to answer. You can, for example, wonder, are these things in the unit ball or not? You can pick some threshold and say I want everyone above. You can say my arms are the entries of a matrix, and I like to have a pure strategy nest equilibrium. You can do game tree search, etc. Just to give you sort of the richness of this area, what people are looking at. Okay, so that's the model for the world. Now, what does it mean to make a learner? So we need to supply 3 ingredients. The first thing is to figure out when we know enough. So the learner interacts with the world, and at some point the learner decides to stop. Right? So we need a rule for that. It looks at the history up until this point, and at some point it decides that's enough. If you haven't decided yet to stop, then you get to do an experiment. Okay, so in every round before the stopping time, you have to supply a sampling rule that says, now I would like a sample from that arm. Okay. That's the sampling rule, and then the algorithm will observe one sample from that arm. And then at the end, if you do stop, you have to recommend one answer. So you give your best guess for the answer, and then the interaction is over. Okay, so if you run a learner in an environment, together they will generate this interaction, which consists of arm, sample, arm, sample, arm, sample, so many times, and then a recommendation for the best answer. Okay, and that's random, of course. So if you run it again, you might see another one. Right? And in particular, the length of this, we don't fix it in advance. That's up to the learner. Okay, so now, yes. Yes. You mean between the regret and the identification worlds? Or? Yes. Yes. Of course, you can play with this. You can observe some neighbors. You can observe subsets, etc. Or even less sometimes. But here, I will always say you pick one arm and you see a sample from it. Yeah, so if you like pictures, the answer is blue or red. And you have to figure out. Yes, yes. But so just to make it maybe very concrete, this is a 2-arm problem. So after a number of samples, you maybe have some empirical estimates and maybe some uncertainty. So what you will be doing is you will have this uncertainty region. You will take a sample, it will shrink in one of the 2 directions, and then it will shrink, and at some point maybe it's contained fully on one color, and then you say, okay, red. I stop and I say red. Okay, so at this point there are still 2 things that we could care about, namely, how many samples do you take, and did you give the right answer or not? Okay, so it's two objectives. We need to do something to make it a single objective problem. And there are 2 choices, the one you focus on. And here we will focus on what's called the mixed confidence regime. You can also think of that as back learning, if you want, or caring about. Oh, okay. So what you do there is you say, no, I will fix the probability that you make an error, and I'll try to optimize the sample complexity. Okay, so we'll fix with some number delta the probability that you make an error. So your algorithm has to always work. For every bandit model, it has to not make a mistake too much. And then, given that constraint, we will optimize the sample complexity, which we will take here to be the expected stopping time. Okay, so now we have a single objective, sample complexity, and we want to optimize it over all delta correct strategies. Okay, so the other choice you can also do, you can fix the time and see how small you can make the error. That's called fixed budget, but I won't talk about it. Okay, so now, let's first, yes. No. You think so, and that one is wrong. Yeah. That might be true, yes. But somehow the argument of the KL flip, yeah, okay. Similar, yeah, okay. Alright, so now we define sort of a very crisp problem. I want among all delta correct strategies the one that minimizes the sample complexity. Next we're going to look at, can you say that your sample complexity needs to be at least so and so high? Whatever algorithm you have. Right? That's a barrier that we cannot cross, and that if we can meet it, we would be really happy, because then we're optimal. Okay, so how do you build lower bounds? And I'll show you in a moment what the lower bound is, but I think the intuition is more important. So you think about some data, some observations, some history so far, and you think, well, these observations are actually likely under two models, mu and lambda. They both give some reasonable probability to what happened so far, but they disagree in the correct answer that I should give on them. Right? If that happens, then on that data, it's very dangerous to stop, because you could be in either. And in one of them, whatever you do, one of them you will give the wrong answer. Right? And you can't give the wrong answer a lot. So you should probably carry on a bit more if that happens. Otherwise you make a mistake. Alright, so let's write that down and make it a form of statement. So we will always focus on the true model and call it mu. And then we can think about what alternatives are there that are confusing models that we have to rule out unless we make any mistakes. So I call those neg I. Those are the worlds in which the answer is not I. Okay, so there is a correct answer for mu, and neg of that correct answer is all the worlds on which the correct answer is something else. Right? And if they are still plausible, or if they could have as well generated my data, then maybe I should keep on going. Okay, so you can sort of make this, make this formal, make it a nice optimization problem, squeeze it to the max, and you get the following statement. So if you are a delta correct strategy, then no matter what bandit model I put you in, you have to take at least a certain number of samples. And what's that number like? It has two factors that are sort of products, so they're pretty independent actually. One of them comes from the confidence. So the more confidence you want to be, the more samples you need. That's very reasonable. The other one is determined by the bandit problem that we're in. And it's called the characteristic time. And it itself is defined, well, its reciprocal is defined by an optimization problem, which says look for a good distribution on arms, look for an evil alternative world on which the answer is not the one for mu, and then measure the information distance between mu and lambda weighted according to those weights W. Okay? So if you have seen this before, then you probably got to be friends with it at some point. If you haven't, then at this point you go like, whoa, what are you telling me? But the way I motivate this to myself is you sort of want to convince someone else about the correct answer at mu. So you know the correct answer at mu, but you cannot just tell this to this other person. Instead, you can ship off samples to that person, and you want to be very helpful. So you're going to optimize a very helpful allocation of samples, saying like put most of the samples from this arm, and then some from here and some from here. And your goal is to convince that other person that the correct answer from you is the right one. But that other person has to worry that you should not actually still be in a world that has a different best answer. So that has to be ruled out. And this is the rate at which you gain information about that from these samples. Right? This is the proportion of samples you are shown on arm I. And this is the information distance between the true world and this possibly confusing world. Okay, so this is sort of a teacher quantity in some sense that says push information about the true answer to a referee or something. Sorry? We're now getting to the games-like quantity. Yes. So this says if you want to know how, at the moment it's still a lower bound, but I can already give you the way that the algorithms will actually match this, at least in the dominant term, with no additional constant factor, and there will be maybe some lower order dust. But the goal will be to show that this is actually really determining the complexity of the problem. So that means that if you want to know how hard is the problem, you have to solve a problem like this. And what we will do in a moment is we'll actually also use some of the fallout, not just compute this number, but actually compute those W's and use them to drive our sampling strategy. Okay, because as I said, these W's are really the most informative way to allocate samples across the arms. So if you know that, you probably want to use and follow that allocation. Okay, so just to have some numbers and some examples. So suppose we're in a best arm problem, right? So we want to know the index of the maximum entry, and let's just say 5 arms Bernoulli, and let's make them go 0.4, 0.3, 0.2, 0.1, 0.0. Nice. Right, so the best arm is the first. And you can do the computation and solve this problem, and you see that D star is about 200. And a delta being, let's say, 5% errors, log 1 over delta is 3. So you get the answer that no matter what algorithm you do, if you want to be delta correct everywhere, you need at least 600 samples on this problem. Okay, 600 is 200 times 3. And as an interesting thing, we can also compute what is that helpful allocation for this problem. So you think that, well, you need maybe a lot of samples near the top arms, because there it's sort of difficult to see which one is the best. And the far away ones, with a few samples, you can sort of rule out that they are good. But in this case, what actually happens is you need more samples of the second best than of the best. Right? This has to do with the way the variance decays in a Bernoulli model. For Gaussian, this wouldn't happen, but for Bernoulli, it can happen that the second best you need to sample is more than the best. Right? Okay. Good. So that's the lower bound. Yes. Mhm. Okay, I'm torn because I think it would work, but in experiments it works quite poorly. So we tried it, and yeah, that might be. But there is sort of a secret escape, namely, I'm what your algorithm should be doing is it should, in expectation, sample with rate W. But it might actually be that on some samples it should sample a little bit this way, and on some it should sample a little bit that way. And in expectation it matches the W, but not on individual trajectories. We haven't explored that a lot, but I think that this is what the algorithms that we run actually do. So they take sort of a complicated way to make this expectation be. I mean, I can run it. I will show you how good it works. But it's not stellar. We expected that it would just beat every of our algorithms because it has too much secret information. But that's not what happens. Yeah, I think so. Yeah. Yeah, so the algorithms in sort of a mysterious way outperform it a little bit. Okay, so let's get to the design of these algorithms. Right, so the goal now is we have a lower bound. We can come up with all sorts of ways to design algorithms. Right? If you've been exposed to bandit problems, you're probably thinking of let's make some confidence intervals everywhere and let's try to see which one we should shrink so that we can separate things and top. But unfortunately, that won't get you to move this lower bound. So then you can wonder, okay, maybe I should improve the lower bound. But it turns out it's the other way. So you should have a different style of algorithm design that will meet this lower bound. And it's much more based on the lower bound itself. Okay, so let's design that strategy. So as I said, a strategy is three things. Stopping rule, recommendation rule, sampling rule. So two of them we're going to make a very reasonably standard choice, and the sampling rule will be the interesting one. Okay, so let's get the two default choices out of the way. So when do we stop and what do we recommend? So stopping is in some sense a hypothesis testing problem. We want to see, have we got a lot of evidence that the best the answer for our estimate of the world is correct versus the alternative hypothesis that it's not. Okay, and to measure that, one thing you can do is you can say, okay, let's do a generalized likelihood ratio test. Let's look at all the worlds that have as the best answer the one we currently think versus all the worlds that have some other answer. So that, if you work out what that becomes, is a quantity that's actually quite a lot like the lower bound. But now it's based on mu hat, and there is no optimization over W, but there's just the actual number of samples that you have. Okay, so this is the statistic that we will monitor. So now you have to wonder, okay, what does this statistic do under if I'm right and if I'm wrong, right? But it turns out, I don't know, asymptotically, it's sort of like a chi-square thing, but you want to make it a true guarantee. So you need to have some threshold on it, and the typical shape of that is log 1 over delta, which is the term that we sort of expect, and then some lower order junk, and you can fight really hard about sort of the constants that go here and here. And I just omitted them. There should maybe be a 3 and a 5 or something. But there will be some log t stuff, and some log 1 over delta stuff. Okay, so that's what we put as our threshold on lambda hat. Then whenever this GLRT statistic crosses this threshold, we say we have enough evidence that we know the correct answer, and then we output the answer at the current estimate of the bandit model. Okay, and you can prove that whatever sampling rule you pair with this recommendation and stopping rule, you will be delta correct. Just because this test it's not really active. It's sequential, but the active part is all in the same. Okay. So, how about the sampling rule? So that's the interesting bit. So, the sample complexity lower bound was governed by this max-min problem. Okay. And you can see that if you want to match this, you actually have to more or less sample in expected proportions with the arc maximum, the W star. Okay, so that's our hint. That's what an oracle strategy that you're sort of constructing here is doing. So let's try to do that ourselves. Okay, so the problem is that we need to compute this W star at mu, and we don't know mu. So we can't just directly follow W star. So we need to do some estimation. Okay, but some maybe simple idea is to just do a plug-in estimate. So we estimate mu hat, we compute its corresponding W star, and then we try to sample with those proportions. Right? So you can, for example, sample your arm from that W star. Okay? So does that work? Well, with some extra frills here and there, you can actually make that work. Okay, so let's go over what you need to do. So the first thing you want is that you're actually getting to W star of mu. So you really want mu hat to converge to mu. That means you have to sample everyone in the long run infinitely often, which you can do, for example, by allocating some lower order fraction of your samples to everyone. So once you reach a new square root t, a new integer with square root t, you sample everyone once. Okay, so that is enough to ensure that your estimates converge. The next thing you want to do is that you're converging your estimates, but you also need that the W that you get as a result is also converging. Right? So that requires continuity of W star, which in the original paper was actually an assumption. And you can be very subtle about it, and I won't. So we will just assume that it's continuous. It's actually true, but not in the sense you expect. Okay, so that means that the W stars of your mu hats also convert to the W stars of mu. Then W stars are distributions, and you have to play an arm. So you have to have a way to sort of disambiguate a W star to the choice of an arm. Right? And one way to do it is called seed tracking. You just sum up all the W's that you computed so far. So that those are the counts you would have had if you were allowed your fractional counts. But you have these integer counts, and you wanted the sum of the W's. So let's just make sure that that is close to that by making the one that is furthest behind and sampling it one more time. Okay, so that ensures that these are actually extremely close, like a constant. Okay, so in the end, what that ensures is that your sampling proportions tend to W star of mu. Okay, so together with the GLR stopping and recommendation rule, that scheme is called track and stop. Okay. So it inherits the correctness from the GLR stopping recommendation rule. So what we still need to argue is that it matches the lower. Okay. So this was shown for best arm in the Carrier and Kaufman paper, and then we sort of extended that a little bit, and we show that this scheme for arbitrary queries has asymptotically optimal sample complexity. Okay, so you match at least asymptotically, meaning for delta going to 0, you match the lower bound. So they did it for best arm, and we introduced like arbitrary queries. And in principle, the continuity assumption actually, once you go beyond best arm, it will break at some point, but in a fixable way. So we fixed it, and as a result, we could show it for lots of other queries. Since you're asking, in this paper there were 2 tracking rules proposed, and they proved that both work. So we showed that one of them actually doesn't work beyond best arm, and this is exactly for this continuity trick. Yes. That will be right next. Yes, but I think it might be for after the break. It will also be next. Also next. Yes. So I think it might be a good point for the break. Let me just peek ahead. Yes. Yeah, there are 3 minutes left. But no, so C is for, I mean, I can explain. It relates to things that we've heard before. So, you know, as you're going along and sampling, your mu head becomes more and more accurate. And this C tracking says, sum up all the W stars that you got in the past. But these are all based on bad estimates